Let the curve y is equal to f of x be a differentiable real function on the interval I. Consider a point P, x, y on the curve, and a point Q close to point P such that its coordinates are x plus delta x, y plus delta y. Here, delta x is a small increment in x and delta y is the increment in y corresponding to the increment in x. From the figure, y plus delta y is equal to f of x plus delta x, and y is equal to f of x. This gives us delta y is equal to f of x plus delta x minus f of x. Dividing both the sides by delta x, we get the equation as shown. Denote this by equation 1. Assume that limit of delta y upon delta x exists as delta x tends to 0. So, applying limits on both the sides of equation 1, we get limit of delta y upon delta x as delta x tends to 0 is equal to limit of f of x plus delta x minus f of x whole divided by delta x as delta x tends to 0 using first principles. The right-hand side of the equation can be written as dy upon dx. Therefore, limiting value of delta y upon delta x is dy upon dx. Hence, delta y upon delta x is equal to dy upon dx plus epsilon, where epsilon is a small positive quantity. Multiplying both the sides by delta x, we get delta y is equal to dy upon dx into delta x plus epsilon into delta x. Since the values of epsilon and delta x are very small, the product of these two quantities is negligible. Hence, the approximate value of delta y is dy upon dx into delta x. That is, the increment delta y in the dependent variable y is approximately equal to dy upon dx multiplied by delta x. We have f of x plus delta x is equal to delta y plus f of x. The approximate value of the function is equal to the sum of the approximate increment value in the function f of x. The differential of the dependent variable, that is dy, is approximately equal to its increment, that is delta y. The differential of the independent variable, that is dx, is equal to its small increment, that is delta x. Velocity is the rate of change of distance with respect to time. In terms of derivatives, velocity can be defined as ds upon dt. Similarly, acceleration is defined as the rate of change in velocity with respect to time. Thus, dv upon dt is equal to the derivative of ds upon dt, which will be further equal to d square s upon dt square. Observe that in both the cases, a certain quantity is changing with respect to time. This change in one quantity with respect to time is known as rate of change. If a quantity y varies with respect to another quantity x, satisfying y is equal to f of x, then dy upon dx represents the rate of change of y with respect to x. Let x and y be two distinct functions of time. In this case, The rate of change of y with respect to x can be calculated by using the ratio of rate of change of y and the rate of change of x, each with respect to time t. Or dy upon dx is equal to dy upon dt into dt upon dx. The rate of change of y with respect to x at x is equal to x naught is given by dy upon dx at x is equal to x naught. Let us see an example now. The side of a square is increasing at the rate of 0.02 centimeters per second. What is the rate at which the area is increasing? When the side of the square is 6 centimeters. Let S be the side and A be the area of the square. Given that the side of the square is increasing at the rate of 0.02 centimeters per second, this implies ds upon dt is equal to 0.02. We know that the area of a square of side S is S square. The rate of change of the area of square A is given by dA upon dt. Thus, dA upon dt is equal to d of S square divided by dt. On simplification, dA upon dt is equal to 2s into ds upon dt. Given that the side of the square is 6 centimeters and ds upon dt is equal to 0.02, hence dA upon dt is equal to 2 into 6 into 0.02, that is 0.24. The rate of change of area of the square is 0.24 centimeters square per second. The positive sign of dy upon dx indicates that y increases as x increases. The negative sign of dy upon dx indicates that y decreases as x increases. Take a look at the graph of f of x is equal to sin x. If you observe the graph carefully between 0 and pi, you will see that as x increases from 0 to pi by 2, sin x increases from 0 to 1. That is, the height of the graph increases as we move from 0 to pi by 2 on the x-axis. And as x increases from pi by 2 to pi, sin x decreases from 1 to 0. In other words, the height of the graph decreases as we move from pi by 2 to pi on the x-axis. Now, what do you conclude out of this discussion? Is f of x is equal to sin x an increasing function or a decreasing function? Let's see the analytical definition of an increasing or decreasing function on an interval to answer this question. Let I be an open interval contained in the domain of the real-valued function y is equal to f of x. Then, f is said to be an increasing function on interval I if x1 less than x2 in I, which implies that f of x1 is less than or equal to f of x2 for all x1, x2 in I. However, if f of x1 is strictly less than f of x2 for all x1 less than x2 in I, then f is said to be a strictly increasing function. The graph of an increasing function is as shown. The straight line in the graph depicts that at some points, the value of the function remains constant with the increase in the value of x. That is, for some x1 less than x2, we have f of x1 is equal to f of x2. Hence, this function is not strictly increasing. Take a look at the graph of the function. F of x is equal to x plus 2. For every value of x, we get a different value for f of x. And as the value of x is increasing from -1 to 2, the value of f of x is increasing from 1 to 4. So, for every x1 less than x2, we have f of x1 less than f of x2. Hence the function f of x is equal to x plus 2 is strictly increasing on the set of real numbers. Now, let us see when a function is said to be decreasing or strictly decreasing on an interval. A function f is said to be a decreasing function on the interval I. If x1 less than x2 implies that f of x1 is greater than or equal to f of x2 for all x1, x2 in I, and f is said to be a strictly decreasing function on the interval I if for every x1 less than x2 we have f of x1 greater than f of x2 for all x1, x2 in I. Here is the graph of a decreasing function. The straight line on the graph depicts that with the increase in the value of x, the value of the function remains constant at some points. That is, at a few places, f of x1 is equal to f of x2, though x1 is less than x2. Now, consider the function f of x is equal to minus x plus 2. The graph of the function is as shown. Observe that as the value of x increases from -1 to 2, the value of f of x decreases from 3 to 0. So, as the value of x increases, the value of the function decreases. So, for every x1 less than x2, we have f of x1 is greater than f of x2. Hence, f of x is equal to minus x plus 2 is a strictly decreasing function on the set of real numbers. Now, let's get back to the graph of the sine function and see whether it is a decreasing function or an increasing function. We know that the domain of sine x is the set of real numbers and its range is the closed interval -1 to 1. Let I1 and I2 be two open intervals defined on the set of real numbers as shown. If we consider any 2 points, x1 and x2 between 0 and pi/2, such that x1 is less than x2, then f of x1 is less than f of x2. This implies sine x is strictly increasing on interval I1. However, if we consider any 2 points, x1 and x2, between pi/2 and pi, such that x1 is less than x2, then f of x1 is greater than f of x2. This shows that sine x is strictly decreasing on interval I2. This means that sine x is partly increasing and partly decreasing on domain R. Hence, we can conclude that sine x is neither increasing nor decreasing on R. You have already learned to find the nature of a function in a given interval. Let's extend the concept to determine the nature of a function at a given point. Consider a real-valued function f defined on an open interval I. Let us find the nature of the function at a point x1 in the open interval I. The nature of the function at point x1 is the same as the nature of function in the open interval containing x1. Let h be a small positive real number. Consider an open interval in the neighborhood of x1, that is, open interval x1 minus h, comma, x1 plus h. Function f is said to be increasing, or strictly increasing, or decreasing, or strictly decreasing at point x1 if it is increasing or strictly increasing, or decreasing or strictly decreasing, respectively, in the open interval x1 minus h, comma, x1 plus h. Now, we will state and prove a theorem based on the nature of a function at a given point in the domain of the definition of the function. Let a function f be continuous on closed interval a comma b and differentiable on the open interval a comma b. Then the function f is said to be increasing or decreasing depending upon whether its derivative is greater than or equal to 0, or less than or equal to 0, respectively. And the function is a constant function if its derivative is 0. Let us prove the theorem now. Consider two arbitrary elements, x1 and x2, such that x1 is less than x2 in the closed interval a comma b. By the mean value theorem, there exists an element c in the open interval x1 comma x2 such that the derivative of f at point c is equal to the value of f at x2 minus the value of f at x1 upon x2 minus x1. Let's consider that the derivative of f at point c is greater than or equal to 0. This implies that the right-hand side of equation 1 is greater than or equal to 0. On simplifying, we get f of x1 is less than or equal to f of x2. This shows that the function is increasing. Now, we will prove the second part. In this case, we will take the derivative of f at point c less than or equal to 0. This implies that the right-hand side of equation 1 is less than or equal to 0. On simplifying, we get f of x1 is greater than or equal to f of x2. Hence, we can say that the function is decreasing. Now, we will prove the last part. In this case, let's consider that the derivative of f at point c is equal to 0. This implies that the right-hand side of equation 1 is equal to 0. On simplifying, we get f of x2 is equal to f of x1. This equality is true for all values in the closed interval a comma b. This implies that the function has a constant value for all the values in the interval. Hence, the function is a constant function. This theorem leads us to some important results. Let's take a look at them. A function f is said to be strictly increasing in an open interval a comma b if its derivative is greater than 0 in that interval. A function f is said to be strictly decreasing in an open interval a comma b if its derivative is less than 0 in that interval. A function f is increasing or decreasing on R if it is increasing or decreasing in every interval of R. Let P be a point on the curve and Q be the neighboring point of P on the curve. The line that passes through points P and Q is known as a secant to the curve. Fix point P and move point Q towards P along the curve such that it comes very close to P. The limiting position of the secant is known as tangent to the curve. Here P is known as the point of contact. Let the equation of the curve be y is equal to f of x. Let P, a comma b be a point on the curve, and and m be the slope of the tangent at P. We call that the slope of a tangent to the curve y is equal to f of x at point P, x1, y1 is dy upon dx at x1, y1. And the equation of a line passing through a point x1, y1 and having slope m is y minus y1 is equal to m into x minus x1. Therefore, the equation of the tangent to the curve y is equal to f of x at point P, a, b is given by y minus b is equal to dy upon dx at P into x minus a. This can also be written as y minus b is equal to f dash a into x minus a. If the tangent to the curve y is equal to f of x makes an angle theta with the positive direction of the x-axis, then the slope of the tangent dy upon dx is equal to tan theta. We know that the slope of a horizontal line is 0. So, if dy upon dx at P is equal to 0, then the tangent line at P is parallel to the x-axis. In this case, the tangent line is parallel to the x-axis. Hence the equation of the tangent line is y is equal to b. If dy upon dx at P does not exist, then the tangent line at P to the curve is a vertical line through P. In this case, the tangent line is perpendicular to the x-axis. Hence the equation of the tangent line is x is equal to a. Let us recall that a normal to a curve is a line that is perpendicular to the tangent at the point of contact. Let line L be the tangent to the curve y is equal to f of x at point P, a, b. Let n be the normal to the curve at P. We know that the slope of a tangent L is f dash a. This implies the slope of normal n is equal to minus 1 upon f dash a, as the product of the slopes of two perpendicular lines is equal to minus 1. The equation of the normal to the curve at the point P, a, b is y minus b is equal to minus 1 upon f dash a into x minus a. On simplifying, we get the equation of the normal as y minus b into f dash a plus x minus a is equal to 0. If dy upon dx at P does not exist, then the normal at the point P, a, b is parallel to the x-axis and its equation is y is equal to b. If dy upon dx at P is equal to 0, then the normal at the point P, a, b is parallel to the y-axis and its equation is x is equal to a. Consider the graph of the function y is equal to f of x with domain D, the subset of real numbers. It is clear that the value of the function f at a point A is the maximum. That is, the value of the function at any other point to the left or right of A is less than f of A. Mathematically, a function f is said to have a maximum value at a point A in its domain if the value of the function at that point is greater than or equal to the value of the function at any other point in its domain. The number f of A is called the maximum value of f in D, and point A is called the point of maximum value of f in D. Now take a look at this graph. What do you observe? Yes, you got it right. In this case, the value of the function f at point A is the least. That is, the value of the function at any other point to the left or right of a is greater than f of a. Mathematically, a function f is said to have a minimum value at a point a in its domain if the value of the function at that point is less than or equal to the value of the function at any other point in its domain. The number f of a is called the minimum value of f in D, and point A is called the point of minimum value of f in D. If a function f has either the maximum value or the minimum value at a point A in its domain, then f is said to have an extreme value at that point. In such cases, the number f of a is called an extreme value of f in D, and point A is called an extreme point. Consider the function f of x is equal to 2x squared for all x belonging to the set of real numbers. Let us find the maximum and minimum values of this function in the domain R. The graph of the given function can be drawn as shown. Now, observe the graph carefully. The value of the function f at the point 0 is 0, and f of x is always greater than or equal to 0 for all real values of x. Therefore, the minimum value of the function is 0, and the point of minimum value of f is x is equal to 0. It may also be observed that there is no maximum value for this function, since the value of the function increases as x increases from 0, and also the value of the function increases as x decreases from 0. However, if we restrict the domain of function f to some closed interval, then its maximum value also exists. Let's verify this. Suppose the domain of function f is restricted to closed interval -2, 1. Then, the maximum value of the function is 8, which is at x is equal to -2. Let us consider another example. Let f of x is equal to modulus x plus 2 be a function defined for all x belonging to the set of real numbers. Let us find the maximum and minimum values, if any, of this function. The graph of the given function can be drawn as shown. Observe that the value of function f at x is equal to -2 is 0. Also observe that for all real values of x, the value of the function is always greater than or equal to 0. Therefore, the function f has a minimum value of 0, and the point of minimum value of f is -2. Also observe that the function f has no maximum value in the set of real numbers, and hence no point of maximum value in the set of real numbers. However, if we restrict the domain of function f to some closed interval, then its maximum value also exists. For example, let us restrict the domain of the function f to closed interval -3, 1. In this case, the maximum value of the function is 3, which is at x is equal to 1. If you notice, you will observe that the function is not differentiable at x is equal to -2. This shows that a function has an extreme value at a point even if it is not differentiable at that point. In both the examples discussed, we saw that if we restrict the domain of the function to some closed interval, then the maximum and the minimum values of the functions exist. This discussion leads us to a result which states that every increasing or decreasing function assumes its maximum or minimum value at the endpoints of the domain of definition of the function. More generally, it can be stated that every continuous function on a closed interval has a maximum and a minimum value. Now, let's proceed further and learn about local maxima and local minima of a function. Take a look at the figure here. Observe that the curve of the function is increasing from point O to P, Q to R, and S to T, whereas it is decreasing from P to Q, R to S, and T to U. The points at which the nature of the function is changing from increasing to decreasing or from decreasing to increasing, that is, points P, Q, R, S, and T, are known as the turning points or stationary points of the given function. Also, if you observe the graph carefully, you will notice that the function has minimum values in some neighborhood of points Q and S, and has maximum values in some neighborhood of points P, R, and T. The points P, R, and T are called the points of local maximum, and the values at these points, that is, the y-coordinates of points P, R, and T, are the local maximum values of f of x at these points. Similarly, the points Q and S are called the points of local minimum, and the values at these points, that is, the y-coordinates of points Q and S, are called the local minimum values of f of x. The local maximum value and the local minimum value of a function are referred to as the local maxima and the local minima, respectively, of that function. Let us now define local maxima and local minima mathematically. Let f be a real valued function and let c be any point in the domain D of f. Then, C is called a point of local maxima if there is an h greater than 0, such that f at C is greater than or equal to f at x for all x in open interval c minus h, c plus h. The value f of c is called the local maximum value of f. Also, C is called a point of local minima if there is an h greater than 0, such that f at C is less than or equal to f at x for all x in open interval c minus h, c plus h. The value f of c is called the local minimum value of f. Let us now understand the concept of local maxima and local minima graphically. Let the point of local maximum value of f be x is equal to a. Then, the graph of the function f around a is as shown. Here function f is increasing in the open interval a minus h, a, and is decreasing in the open interval a, plus h, where h is a small positive number. we have the derivative of the function at a is equal to 0. Now, let x is equal to a be the point of local minimum value of f. Then the graph of the function f around a is as shown. In this case, f is decreasing in the open interval a minus h, comma a, and is increasing in the open interval a, comma a plus h, where h is a small positive number. This means that the derivative of f towards the left of a is less than 0, and the derivative of f towards the right of a is greater than 0. Therefore, the derivative of f at point a is equal to 0. In view of the discussion, we can state a theorem. Let f be a real-valued function defined on an open interval I. Suppose point A is any arbitrary point in I. If f has a local maxima or a local minima at the point x is equal to a, then either f dash a is equal to 0 or f is not differentiable at a. The proof of this theorem is beyond the scope of this lesson. However, remember that the converse of this theorem need not be true. That is, a point at which the derivative vanishes need not be the point of local maxima or local minima. In the previous lesson, we exhibited that the graphs of certain functions help us to find the maximum value and the minimum value of those functions. For example, from the graph of f of x is equal to 2x squared, it can be easily deduced that the value of the function f at point 0 is 0, and that the value of the function is always greater than or equal to 0 for all real values of x. This means that the minimum value of the function is 0, and the point of minimum value of f is x is equal to 0. Also, there is no maximum value for this function, since the value of the function increases as x increases from 0, and also the value of the function increases as x decreases from 0. In addition to this method, there is another method known as the first derivative test, which is quite frequently used to find the minimum or maximum value of a function. Let's learn about this method step by step in detail and find the local maxima and the local minima of the function f of x is equal to 2x squared. The first step is to find the derivative of the function f of x. The derivative of the function f of x with respect to x is equal to 4x. After finding the derivative, we equate it to 0 and solve it for the roots of f dash x equal to 0. On equating the derivative to 0, we get only one root, and that is x is equal to 0. The roots so obtained are known as the critical points or stationary points of x. At these critical points, we find the local maxima or local minima of the function f by observing the behavior of the function in their small neighborhood. If the derivative of f is positive at the left neighborhood values of a1, and if the derivative of f is negative at the right neighborhood values of a1, then x is equal to a1 is the point of local maxima. Similarly, if the derivative of f is negative at the left neighborhood values of a1, and if the derivative of f is positive at the right neighborhood values of a1, then x is equal to a1 is the point of local minima. Let's now get back to the problem. In this case, there is only one critical or stationary point. Let us now observe the behavior of the function in a small neighborhood of 0. The sign of the derivative of function f is negative when the value of x is slightly less than 0. Also, the sign of the derivative of function f is positive when the value of x is slightly more than 0. It means that the derivative of the function f changes its sign from negative to positive when x increases from the left neighborhood of 0 to the right neighborhood of 0. Hence, we can say that x is equal to 0 is the point of local minima. This discussion leads us to the mathematical definition of local minima and local maxima. Let f be a function defined on an open interval D. Let f be continuous at a critical point A in D. Then, if the derivative of f changes its sign from negative to positive as x increases through point A, then A is the point of local minima. Here, the local minimum value of the function is its value at A. If the derivative of f changes sign from positive to negative as x increases through point A, then A is known as the point of local maxima. Here, the local maximum value of the function is its value at A. Now, take a look at this graph. In the diagram, the tangent line is horizontal at 0, 1, and the slope of the curve is 0 on both sides of this point. That is, f-x does not change its sign as x increases from the left neighborhood of 0 to the right neighborhood of 0. So in this case, 0 is neither a point of local maxima nor a point of local minima. Such a point, which is neither a point of local maxima nor a point of local minima, is known as the point of inflection. Mathematically, if the derivative of x does not change its sign as x increases through A, then A is neither a point of local maxima nor a point of local minima. Such a point is called the point of inflection. Now, let us take a quick look at the steps to be followed to find the local maxima or minima using the first derivative test. Let us now geometrically define local maxima and local minima with the help of graphs using the first derivative test. This figure shows the graph of a continuous function f defined on an open interval I. Let A be any critical point in I. Here, we can observe that the derivative of f is negative at every point sufficiently close to and to the left of A. Similarly, the derivative of f is positive at every point sufficiently close to and to the right of A. That is, the derivative of f changes its sign from negative to positive when x increases through A. In such situations, point A is known as the point of local minima. Now, let us look at another figure. This is the figure of a continuous function f defined on an open interval I. Let A be a critical point in open interval I. As per the figure, the derivative of f changes its sign from positive to negative when x increases through A. That is, the derivative of f is positive at every point sufficiently close to and to the left of A. Similarly, the derivative of f is negative at every point sufficiently close to and to the right of A. In such situations, point A is known as the point of local maxima. Consider a function f of x is equal to 2x minus 1, where x belongs to the open interval minus 2, 2. The ordered pairs satisfying the function f of x are minus 1, minus 3, 0, minus 1, and 1, 1. With these ordered pairs, the graph of the function can be obtained, which is as shown. Let's now jot down all the observations that we get from this graph. Since there are no gaps or breaks in the graph, the function f of x is continuous on the given interval. The derivative of f is equal to 2, which is greater than 0. Therefore, f is strictly increasing on the open interval minus 2 to 2. The given interval on which f is defined is an open interval. This means f is not defined at the end points of the interval. Therefore, f has neither a maximum value nor a minimum value. Also, there are no turning points in the graph. So f has neither a local maximum value nor a local minimum value. Let us now see if there is any alteration in the observation. If we extend the interval from open interval minus 2, 2 to closed interval minus 2, 2. Now, the ordered pairs satisfying the function f of x are as shown. If you observe the graph in this case, it is defined at the endpoints too. So, the continuity and the differentiability of the function remain unaffected. However, it certainly does have a maximum and a minimum value. The minimum value of the function f is minus 5, and it is attained at x is equal to minus 2. And the maximum value of f is 3, which is attained at x is equal to 2. However, function f still doesn't have local maximum and minimum values, as there are still no turning points in the curve. The maximum value 3 of f at x is equal to 2 is also called the absolute maximum value, or the global maximum, or the greatest value of f on the closed interval minus 2, 2. Similarly, the minimum value minus 5 of f at x is equal to minus 2 is called the absolute minimum value, or the global minimum, or the least value of f on the closed interval minus 2, 2. Let us learn to find the absolute maximum and minimum values of a function on a closed interval. Consider the graph of a continuous function defined on a closed interval x1, x8. Observe that the function has local minima at the points x2, x4, and x6, and the corresponding minimum values are the values of the function at these points. Also, local maxima occur at the points x3, x5, and x7, and the corresponding maximum values are the values of the function at these points. The absolute minimum value of the given function is the minimum of all the values of the function at these critical points as well as at the end points. Also, the absolute maximum value is the maximum of all the values of the function at these critical points as well as at the end points. Mathematically, a function f defined on a closed interval I is said to have absolute minimum value at a point C in I if f of c is less than or equal to the value of f at any other point on I. The number f of c is called the absolute minimum value of f on I. Similarly, a function f defined on a closed interval I is said to have absolute maximum value at a point C in I if f of c is greater than or equal to the value of f at any other point on I. The number f of c is called absolute maximum value of f on I. Let us now learn some important results that will help us find the absolute minimum and absolute maximum values of a given function. Let f be a continuous function defined on a closed interval. Then, f attains the absolute maximum value and the absolute minimum value at least once in that interval. Let f be a differentiable function on a closed interval. Function f is said to attain absolute maximum value or absolute minimum value at a point alpha in that closed interval if the derivative of f at alpha is equal to 0. Local maxima and local minima of a function occur alternately, which means that between every two local maxima there is one local minima and vice versa. Local minima at some points may be greater than local maxima at some other points. Let us now apply what we have learned so far to find the absolute minimum and maximum values of a function f on the closed interval -1, 2. To find the required values of the function f, we have to first find its critical points, which are obtained by equating the derivative of the function to 0. This gives 4x into 3x minus 4 is equal to 0. This implies that x is equal to 0 and x is equal to 4 upon 3 are the two critical points. Next, we find the value of the function at these points. The value of the function f at x is equal to 0 is 1. The value of the function f at x is equal to 4 upon 3 is minus 101 divided by 27. Also, we find the value of the function at the endpoints of the interval. We get f of -1 is equal to -11, and f of 2 is equal to 1. The absolute maximum value is the maximum of all the values of the function at these critical points as well as at the end points. Thus we conclude that the absolute maximum value of f on the closed interval -1, 2 is 1, occurring at x is equal to 0 and x is equal to 2. Also, the absolute minimum value is the minimum of all the values of the function at these critical points as well as at the end points. Thus, the absolute minimum value is -11, which occurs at x is equal to -1. Hence, the absolute maximum and minimum values of the given function on the given interval are 1 and -11 respectively. Let us now learn the working rule to find the absolute maximum and absolute minimum values of a function f on a closed interval a, b. First, find the derivative of the given function. Then, find all the critical points of the function by solving the equation obtained by equating the derivative of the function to 0. After that, find the value of the function at all the critical points and also the value of the function at the end points. Now, the absolute minimum value of the function is the minimum of all the values of the function at all critical points as well as at the end points. Similarly, the absolute maximum value of the function is the maximum of all the values of the function at all critical points as well as at the end points. Recall the first derivative test. It states that if the derivative of f changes its sign from negative to positive as x increases through a point A, then A is the point of local minima. And the local minimum value of the function is the value of function f at A. Also, if the derivative of f changes its sign from positive to negative as x increases through a point A, then A is the point of local maxima. And the local maximum value of the function is the value of function f at A. In addition to the first derivative test, there is another test known as the second derivative test, which is quite often used to determine the local maxima and local minima of a function. Let's learn about this test in detail. Consider a function f defined on an interval I. Let A be any arbitrary element in the interval I. Let us suppose that the given function f is differentiable at A twice. If the first derivative is equal to 0 and the second derivative is negative, then A is the point of local maxima, and the local maximum value of the function is f of A. Also, if the first derivative is equal to 0 and the second derivative is positive, then A is the point of local minima, and f of A is the local minimum value of the function f. The second derivative test fails if both the first and the second derivatives are equal to 0. Let's prove the first part. Given that the derivative of f at point A is 0 and the double derivative is negative at point A, using the first principle of derivatives, the second derivative of f at point A can be defined as shown. we have that the first derivative of f at point A is equal to 0. For a sufficiently small h, the first derivative of f, a plus h, upon h will be less than 0. Now two cases arise. The value of h may be either negative or positive. Suppose the value of h is negative, then the first derivative of f at the point a plus h should be positive. Suppose the value of h is positive, then the first derivative of f at the point a plus h should be negative. Observe that as the value of h is increasing from negative to positive, the value of the corresponding first derivative is decreasing from positive to negative. Hence, from the first derivative test, the function has a local maximum at point A. The value of the function at point A is local maximum value. Similarly, we can prove the second part. The second derivative test fails if the second derivative is also 0. In this case, we follow the first derivative test. Now, let us learn the working rules to find the local maximum and local minimum values. Begin by finding the derivative of the first function and equate it to 0. Suppose the values of x are x1, x2, x3, and so on. Then, find the second derivative of the given function. After that, find the values of the second derivative at points x1, x2, x3, and so on. If the values of the second derivative at these points are negative, then the function has local maximum values at these points. If the values of the second derivative at these points are positive, then the function has local minimum values at these points. Local maximum or local minimum value is the value of the function at these points. Let's learn this with the help of an example. Let f of x be a function given by 2x cubed minus 21x squared plus 36x minus 20. We have to find the local maximum or local minimum values of this function. On differentiating with respect to x, we get the derivative as 6 into x squared minus 42 into x plus 36. For function f to have local maxima or local minima, its derivative should be equal to 0. On simplifying, we get the equation as x squared minus 7 into x plus 6 is equal to 0. Solving the equation, we get the values of x as 1 and 6. Now, we will find the second derivative. The second derivative of f is equal to 12x minus 42. The value of the second derivative of the function at x is equal to 1 is minus 30. This shows that the second derivative of f at 1 is negative. Hence, the function has local maximum value at x is equal to 1. Hence, the local maximum value of the function is minus 3. The value of the second derivative of the function at the value of x is equal to 6 is 30, which is a positive value. Hence, the function has local minimum value at x is equal to 6. The local minimum value is minus 128.